Hello, and thank you for joining us again at Highwater Studios. Today we're going to be continuing our discussion on the review for the Fundamentals of Engineering exam for environmental engineers. Today we're going to be talking about risk assessment, and I know this is a topic that often glazes people's eyes over, but it actually can be very interesting in terms of society and psychology and economics and what people are interested in spending money on to reduce risks versus other, reductions of risk. So there's a lot of interesting things there that we won't be talking about today. Instead, we'll be focused purely on the Fundamentals of Engineering exam and the questions that you're probably going to see. So, starting out, we're going to discuss some topics on terminology, and then we'll go through a few examples. Okay, so risk assessment. What is risk assessment? Basically, we're talking about what is the risk for a human developing some kind of either organ damage, basically, or cancer. It kind of gets split into two categories. You have your carcinogens and you have your non-carcinogens. And so, discussing this, we usually use some terminology based on the number of responses per population of test subjects. And so, just kind of jumping right into the terminology here, we have our NOEL, and sometimes the A will not be there, but basically no observed adverse effect level. Excuse me, sorry. So what this means is this is a concentration, this is the highest concentration where there was no adverse effect in the test population. So if you're testing mice, they didn't get cancer, they didn't have liver damage, whatever would be the adverse effect there. Sometimes you have low L, which is lowest observed adverse effect level, and this basically means whatever your data are, this is the lowest level that showed some kind of adverse effect, cancer, damage, whatever, reproductive harm. Normally you don't want to use low L. You basically only use that if you don't have a NOEL. Obviously, you want to use NOEL. Whatever would give you some confidence that you're not going to harm the population, right? But sometimes that's not available. And then what used to be used in risk assessment was the ADI, or acceptable daily intake. And this would be the NOEL, if available, or low L if it's not, divided by a safety factor. Well, we've modified how we look at safety factors. We've kind of gotten more specific in terms of safety factors. So what you're probably going to see nowadays is the reference dose, the RFD. And so the reference dose is your NOEL or low L divided by your uncertainty factor. And you can have a lot of different uncertainty factors based on whether, you're probably going to have a factor of 10 right off the bat, just because humans tend to be very different, right? And we do a lot of these studies with the idea of a adult human in mind, but what about children, right? They have a very low body weight. They also have developing organs, which are much, much, much more susceptible to damage while they're developing. So there's a lot of variability there that if you want to try to protect people, you need to add in a safety factor based on that alone. There could also be uncertainty because most of the time we're extrapolating data from animal studies. We can't test humans. I mean, that's, obviously that's not ethical. So we tend to do studies on animals, and we try to say, like, well, it harmed an animal, so it's probably going to harm a human too. But we don't know how those exactly translate, right? So we need to be, if we wanted to protect people as best as we're able, we need to be, include that uncertainty into our factors when we're talking about translating animal studies to humans. Also, duration of testing tends to be an issue when we talk about studying animals. A lot of these times, the animals don't have the same lifespan that humans do, or we don't, if we're talking about a carcinogen over a person's lifetime of 70 years, roughly, then we can't wait 70 years to get the results, right? We need these quicker so we can make decisions now. And so we try to accelerate these studies and extrapolate them out over a longer period of time. And obviously that's going to cause more uncertainty. So there's a lot of uncertainty factors here. And we account for that by basically applying factors of 10, usually, of uncertainty to lower what we would consider an acceptable daily intake, basically. So that's basically how risk assessment works. In terms of the FE exam, any of these topics could come up. They could be, and also the lethal dose. So this is kind of comes back to variability, something you might get asked about, lethal dose. So lethal dose is, or LD50, is what is the lethal dose in 50% of test subjects. So, obviously, even with mice, you're going to have variability. If you have 100 mice, you expose them to some concentration, what would cause death in 50% of the test subjects? That's kind of how lethality of a contaminant is determined, basically on what causes death in 50% of test subjects. Okay, so another thing you're probably going to see on your FE exam, or I'd be surprised if you didn't, is going to be the dose response curve. And so what this is you have increasing dose on the x-axis, right? So here you have increasing dose in milligrams per kilogram of body weight per day is your exposure. And then response. Response is basically the percentage of test subjects that had a adverse effect. And so what you're probably going to see, and what you would want to see if you were conducting these experiments, is something like, okay, we've got nothing, we've got nothing, we've got something, we've got something, we've got something. So basically here is your slope, but this would be your NOEL. This is your no observed adverse effect level, right? Because if you were using whatever this dose is, there was no observed effect, right? There was nothing happened. Nothing that you could observe actually happened. Now over here, this would be your lowest observed adverse effect level. So hopefully you would have these data, but if you didn't, then you would use your low L. And yeah, I mean, basically that's all there is to it, really. So we'll move forward. Okay, so a couple of examples. If we have, so probably you're going to see some kind of calculation for what is like cancer risk, or what is the CDI, or something, some kind of calculation for risk assessment. And it's probably going to be something along these lines here. Now, remember, there's a difference between cancer risk and non-cancer risk, basically non-carcinogens, because with cancer risk, it's always averaged over a lifetime, where with a non-cancer risk, it's just based on exposure duration. So that's one thing to keep in mind. So in this case, we're talking about a cancer risk. So we have a 60 kilogram person. They are consuming 50 milligrams per day of soil. I know that sounds disgusting, but basically you do breathe soil every day. It just is part of life. And can I get this to stop being weird? No. So 30 milligrams per kilogram of benzene for 50 years. Okay, so what we're probably talking about here is a worker who worked, well, in this case, every day for 50 years. And they were breathing in soil that was contaminated with benzene. The benzene cancer slope factor is 0.029, and it's kind of inverted from consumption. So it's kilograms days per milligram. And with an absorption factor of 1. So in this case, it means that all exposure was absorbed. Basically, we're not going to limit it based on some kind of exhalation that wasn't absorbed or whatever. It's fully absorbed. Okay, so we have a CDI. This is your chronic daily intake. And this is equal to your concentration. In this case, 50 milligrams per day, times your contact rate, which is 30 milligrams per kilogram. So we have the exposure of soil times the actual benzene in the soil. Your exposure frequency, which in this case, because we didn't specify it, we're going to assume this is every day. It's 7 days a week. This could be different if it's like a worker. It might say 5 days, per week. So you'd have to basically 5/7 of a year. Or it could be something like often municipalities use risk assessment for handling toxic waste sites by, ironically, building recreational facilities like a soccer field, right? And if you think about it, how often do you play soccer? Maybe twice a week, right? For a couple hours. So your exposure frequency is really going to be quite low. And from that, your CDI is going to be very low, right? So that actually is a strategy often used to deal with toxic sites, basically make them into soccer fields. So, okay, so blah, blah, blah. Exposure duration is going to be, obviously, how long were you exposed? In this case, 50 years. So if you think about, how long were you working? And then you're going to average that out based on a person's body weight. And so usually we'll use an average male adult body weight of 70 kilograms. It might give you some different value, but whatever. If it doesn't give you something, then it's probably going to be 70. And then lifespan, which again is an average value. Typically it's 70 years, 365 days per year. So if we just check my time. Wow. Okay, 15 minutes already. So if we look at this, we're going to have 50 milligrams per day of exposure. We have 30 milligrams per kilogram of contamination in the soil. We want to convert this from kilograms to milligrams for our body weight. We have 365 days per year of exposure. and then we have 50 years of like how long the person worked or whatever. All right, so then, since we said in this case, for some reason, we're talking about a 60 kilogram person, that's our body weight. We have a 70-year lifespan and 365 days per year that they're alive, I would hope. And then, so the CDI in this case, 1.79 times 10 to the negative fifth milligrams. Woo. Per kilogram day. Okay. So that's the chronic daily intake. This is basically the average amount of contamination in a person's body averaged by their body weight over their lifetime and exposure, because that's, you know, how you deal with cancer. It's not, there's no safe exposure for cancer, right? Any amount of exposure is going to affect your average exposure per lifetime. It's kind of a maybe a little bit confusing, but basically any exposure is going to affect your cancer risk over your life. Unlike non-cancer, which basically if you don't damage your organs, you're probably fine. So, okay. Your risk is going to be equal to your CDI times your slope factor. Now, we haven't actually used that yet, but risk, your actual risk here, or, you know, calculated risk, is going to be 1.79 times 10 to the negative fifth milligrams per kilogram day times our slope factor, which is 0.029 kilogram days per milligram, which in this case is 5.18 times 10 to the negative 7. And this would be considered an acceptable risk. So that's actually something else that might come up in the exam, is what is acceptable risk. And acceptable risk is usually 1 per 1 million, or 1 additional cancer occurrences per million exposures. So if you have a city that has 1 million people and you have something in the water supply that may cause cancer, if it only causes cancer in 1 person over a lifetime, that would be considered acceptable. That's basically, generally, at least in the U.S., how cancer risk is sort of evaluated. Okay, so one more example here. If we have a full-time worker exposed to a compound at 60 milligrams per cubic meter of workspace, and the worker inhales at a rate of 1.5 cubic meters per hour, which is somewhat, maybe a little bit elevated, but maybe if you think about a worker that's maybe doing some kind of physical work, they might be breathing quicker. So, a more active worker might breathe at 1.5 cubic meters per hour with a body mass, again, of 60 kilograms. And in this case, an absorption factor of only 0.6. So they're only absorbing 60% of the concentration into their body. So in this case, we want to take a look at the intake rate, which is going to be the exposure, which is the 60. Oh, I'm sorry. It's actually micrograms. Can't quite see what that is, but that's actually micrograms per cubic meter for this example. Times the rate of exposure, which in this case is going to be 1.5 cubic meters per hour, times the frequency, which in this case we're talking about a worker, so we're going to assume that this is going to be a 40-hour work week, and that's going to translate to 8 hours per day. All right. And then we're going to have an absorption factor, obviously, of only 0.6. And then our CDI is going to be our intake rate divided by our body weight, because body mass obviously is going to dilute, the risk here. So, okay. So our IR intake rate is going to be 60 micrograms per cubic meter times our 1.5 cubic meters of inhalation per hour. Then we're just going to do conversion, and then since we're looking at our intake rate per hour, it's going to affect our exposure frequency, because we're only breathing it, during the workday, or 8-hour workday in this case. And that gives us 0.432 milligrams per day actually absorbed into our body. Now, this is just intake rate. It doesn't matter if you're a full-grown adult or a baby, whatever. It doesn't matter in this case. But when we look at chronic daily intake, now we're basically looking at the concentration in your body. So if we take our intake rate, divide it by our worker's body mass, sorry about that, then we have a CDI of 0.0072 milligrams per kilogram day. And so you could use these numbers. Obviously, you could be asked to calculate this. You could be asked to compare this to a NOEL. You could be asked to determine whether an exposure rate is safe, or any number of questions. But basically, it's all going to kind of stem from these types of calculations. So hopefully that was helpful. And I do definitely appreciate you joining us here at Highwater Studio for another episode on our continuing series of review for the Fundamentals of Engineering exam for environmental engineers. A bit of a mouthful. Thank you very much.